Hello, and welcome to Petabyte Scale Next Generation Sequencing Data, Infrastructure, Operation, and Oversight, sponsored by EMC Isilon. I'm Rebecca Friend, and I'll be moderating this webinar. Our speakers today are Yuhao Lin and Sasha Pagel. You can read their full bios on the right side of your window. Just a few technical notes before we begin. If you have trouble reading a slide, please hold and drag the right corner of the slide window to enlarge. Please also disable your pop-up blocker to participate in the interactive parts of the presentation. And at the bottom of the console, you can select the Download Slides button to view a PDF version of the slide deck. We will follow the presentations with a Q&A session, so please submit your questions during or after the presentations using the Q&A box at the right of your window. All right, let's begin. Sasha, go ahead.
All right, thanks. Make sure I've pushed out the right slide. All right. Hello, good morning, good afternoon, everybody. My name is Sasha Pagel. I'm the Life Sciences Business Development Manager here at Isilon. First off, thank you for making the time today to join our webinar. This webinar is actually a second in a three-part series where we're exploring the different facets of managing and analyzing next-gen sequencing data. And today I'm actually super excited to host Yuhao and have him share his insight and experience with managing next-gen sequencing data at LIlly. Actually, I think the topics he's going to cover are actually very, very timely. In fact, recently I just returned from a trip visiting a number of life science organizations, and as I was reflecting about my visits, they all seem to share a common trait, and that trait was, that their sequence archives are dark. I want to pause here. Actually, I want to thank Guy Coates at the Sanger for really, doing a great job of succinctly summarizing this trait and really being able to use that as an analogy to sum up what's going on. For example, each of the organizations that I visited, and probably as you are, accruing a huge amounts of sequencing data, but a lot of it remains untapped for a variety of reasons. For me, on this last trip and the organizations I visited, one of the things that was blocking the access and the use of data was really the lack of a science data DMZ and even firewall issues, for example. The good news is that also a lot of these groups are using a variety of strategies, like, for example, like iRods to catalog data so you can find it. Globus, actually, Globus Online, to be able to move data between, say, storage endpoints. And so these are all mechanisms to really sort of turn on the lights, if you will, in the archive. And really, this is all about satisfying that demand to really compute across all the data. And as we all know, with this sequencing data, the goal that we all want to achieve is that ideal signal-to-noise ratio, to really get that statistical power to really lead us to the next clue about, say, for example, a particular tumor type. So with that, those brief introductory comments, I'm excited to pass the baton over to Yuhao and have him share his experience at LIlly in terms of managing and moving next-gen sequencing data.
Hey, thanks, Sasha. All right, so I'm Yuhao Lin. I work for LIlly. As Sasha, I manage next-generation sequencing data there. And as Sasha mentioned, this is by no means a solved problem for anyone dealing with large amounts of NGS data. So I'm happy to share this with the community and hope that it moves the community forward in some way. So hopefully I can go to the next slide. Oops. Okay, hopefully you guys are seeing what I'm seeing. I'm on the slide that says scope. I just want to scope this talk a little bit. So this is going to be about the storage and transfer of NGS data, although there's going to be a little bit of reference to computation as well. This is mostly high-performance storage, and it's all pretty clinical at this point. Okay. Okay, so first I just want to give you a sense of scale and expansion that we've had. So in the left hand, you can see that back in 2010, when we were just starting out in NGS, we had a total of 20 terabytes of storage space for all of R&D. And fast forward 3 years, today we're at a petabyte, as the title of this presentation suggests. So we've gone a 50-fold increase in just 3 years. And NGS is definitely the big driver for this. So similarly, for memory, back in 2010, we had a terabyte across all of our computing cluster, and today we have 32 terabytes, so it's a 32-fold increase. So I just wanted to start off with those numbers and go into more details. Okay, so when we first started dealing with NGS data, we decided that we needed a high-performance storage system, and we decided to start out with 200 terabytes of space, which back then we only had 20 terabytes, so this was a 10-fold increase, and we thought, well, this should be good enough for a couple of years, right? Wrong. We ran out of space in about 6 months. Didn't take long at all, and here's why. Here you're looking at the trend of disk usage from April of last year to this month. And it only goes back to April last year because that's when we started tracking this information. And keep in mind, this is after we contained some of the issues that we had early on. So this trend is actually nicer than what we had early on. But what you can see is that on the y-axis is the amount of data in terabytes, and on the x-axis is the time. So you can see when we started out in April of last year, we had just about 400 terabytes of data total. And we peaked in June of this year, and we went up to 800 terabytes. So a year and 2 months, we added 400 terabytes more. So roughly, it does work out that if we only had 200 terabytes of space, it's going to take about 6 months before we filled it. And if only we knew this back then, we might have made some different decisions, but we live and learn. So that's how much space we're using and the trend. Here's something else. If you look at, well, this is what our file system looks like. At any given point, maybe 60 to 70% of the data is actually active data that we need. The other 30 to 40% is waste. And so those are some of the reasons why the file system gets filled up very quickly, and you really need some smart ways to manage all this. Okay, so I'm taking you guys into our journey a little bit. When we first started looking at NGS data, we had these problems. The data was coming in too fast, and the file system was running out of space. So then people were asking, what can we delete, and what can I keep? If I need to keep something, how long do I need to keep it? And what if I need it later? So some of you guys might have lived through this. I think it's probably not too uncommon for people dealing with a lot of NGS data. So I think of this as a big data explosion. Well, what we figured out is in order to answer those questions of what data you need and don't need, you really need to understand the analysis. It's hard to say what you can throw away if you don't know what you need to do with them. And so it was a big help after we had an analysis plan, and we felt a lot more comfortable with identifying the data that we need versus don't need. But the big thing is to only keep the data that you do need. We're talking about a lot of data here, and we simply can't afford to keep everything. So we need to get comfortable with removing stuff that we don't need, and this includes archiving some of the stuff that you might not, it's no longer active, but you don't want to throw it away completely, so you could archive them to cheap storage. I just want to mention that we do this today, not in an automated fashion, but it is being automated. So one of the things that we did early on is took a look at our backup plan. The backup plan was made throughout the entire file system, and it was made before NGS. So we wanted to see if it really made sense for NGS data. And what our backup plan was prior to NGS was that everything was snapshotted and backed up. Snapshot means it's kept on the primary storage for a number of days before being transported to the backup cluster. And we decided that it didn't make sense to do this for NGS data. And our reasoning was that, first of all, those files are really big. So you need a lot of space to keep them around, keep a copy of that. The other thing was that we get our raw data usually from sequencing vendors by hard drives. So we keep those hard drives. So we still have the raw data on the hard drives. So we can get them if we need it, and then we can regenerate the downstream results from those raw data. It would be difficult. I'm not saying it will be easy to regenerate everything, but it is possible. And so that's our backup plan, instead of keeping a copy of everything on high-performance storage. And the likelihood of the loss was very slow, so that's why we're comfortable with this approach. Let's see. So the lesson here was we need to balance risk and cost. If the risk is low, the cost saving is high, then as long as you understand the risks and you have a plan to deal with it and you accept it, then you should be comfortable with taking a little bit of risk. And so we did this about 2 years ago, and it's worked out well for us. Fingers are crossed. Okay. So our file system, the full terabyte, or full petabyte rather, is open and shared across all users. So we don't have a way to control who uses how much. It's basically free for all. And we do this for a couple of reasons. One is just because we're serving research and things move fast. So we want people to get access to storage as we don't want things to slow them down. So that's one reason. But anyway, a side effect to this is users are not actively spending time managing their waste, and it fills up the file system. So what I mean by waste, a couple of examples of that is temporary data. Those should be deleted when they're not needed, but it doesn't always happen. Sometimes we get bad data from vendors, and they're replaced. So the original bad data can go away when the replaced data has been verified, but again, that doesn't always happen. We have potentially a lot of old and inactive data lying around. That takes a big chunk of the file system. And also, if we have large text files that are uncompressed. Okay, so those are some of the examples of unnecessary data that you're seeing. And that's what makes up the 30 to 40% of the unnecessary data that you see on this chart again. And so what can we do to minimize and reduce that? Oh, okay. So I just want to mention that some of this reduction can be automated. For example, for uncompressed large text files, you can detect those and compress them. And also some of the inactive data, you can probably systematically go and find them and do something about them. But not all of it can be automated. So there's going to be some manual intervention involved. So we looked at all the options for dealing with this waste problem. So here are the options that we thought of. So you could mandate the users to spend time to clean things up themselves. you could set a quota at the user level or the directory level. We found it hard to work for us in a research environment because, quite frankly, the criteria are just changing all the time. I'd be interested to know if you got it working for your research environment. Please let me know if you do. Automated management, manual management. Another option is chargeback, where if someone wants amount of space, they need to pay for it. This is an example of something that would slow things down. They need to get approval and that sort of things, and so we don't do that. What we do is a mix of automated management and manual intervention. So our strategy is exactly that. And here's just some examples of what is automated and what's not automated. The automations are fairly new for us. Up to this point, we've been doing things mostly manually to understand what needs to be done. And then once they're kind of standardized, then now is the time to go and automate them. All right. So here's a summary of the things that we do today to manage NGS data. And as I said, everything is manual today, but the green parts that you see are the parts we're automating right now. So as you can see, a large chunk of it is automatable. Okay, now I'm going to switch gears and talk about data transfer. The approach that I'm going to talk about is not these two, but I just wanted to mention these two because they are available to us. So we have a corporate-wide capability using Isilon, and it transfers up to 100 gigabytes. So if you want to share data with someone else, you could send them up to 100 gigabytes, which is usually too small for NGS data. The other thing that we're working to bring online is Aspera. This is a high-speed file transfer protocol for transferring data between 2 points, and it supposedly has a nice user interface. But like I said, it is being worked on as we speak. Okay, so what I'm going to talk about are some tools that we use for uploading and downloading data, and I call these massively parallel data transfer tools. In the best cases, we can get a sustained rate of about 80 megabytes per second. That's actually too fast for our company network. We have a gigabit connection to the internet. So if I'm taking 80 megabytes per second and the total is only about 120 megabytes per second, that doesn't leave a lot for the rest of the company. So we're capped at about 40 megabytes per second during work hours, and then it's unlimited after those hours. So we're actually developing a framework for automatically adjusting the rate, so it'll automatically go up when the work hours are over, and then automatically gets reduced when the work hours come back on. So some of the sources that we download data from are Amazon S3 bucket, NCBI, Geo, and other things. CG Hub hosts TCGA data, and then some vendors some sequencing vendors that we get data from also have allowed us to download data. And the tools that we use, ARIA 2 is an open source download accelerator. We use that a lot. Talk more about that. Sometimes vendors have their own tools for us to use. For example, Complete Genomics had a tool, and also CG Hub has a tool called GeneTorrent to download TCGA data. Okay. For uploading data, for the most part, we're uploading to Amazon S3. Where we want to share data with a collaborator, if we don't want to send hard drives around, or if it's just a tiny file, we'll upload it to our Amazon S3 bucket and then point the vendor to it. They can just download it.
And the tool we use is a Python module called Bado. It is specifically for uploading data to S3 at blazing speeds. So the key to the acceleration is parallelization. And there's parallelization both internally to the tool, as well as you can run multiple instances of the tool to get more speed. So, okay, now I'm going to go to a specific example for maximizing download rate from S3. So let's say you have 50 files in your Amazon S3 bucket, and they're 10 gigabytes each. You want to download it, so you're downloading 500 gigs total. The first thing you want to know is if you download this unencrypted, you get 2 times faster speed than if it was encrypted. So you want to encrypt only if it's required. So if we use ARIA2 to download this data set, you can run 5 parallel ARIA2 commands at once. You'll get a speed of 50 megabytes each. If you run any more than 5, the total rate would not go up. So 5 about maxes out the number of parallel sessions. But then each of those sessions splits into 16 parallel connections. That's actually configurable. You can have more than 16 or less than that. But 16 has worked well for us. So you're getting an average total speed of 75 megabytes per second. This is a sustained rate. So you can finish those 500 gigs pretty quickly, a few hours. There are some side effects to these massively parallel download tools. One is that ARIA2 will produce network overhead if you do a lot of different connections. So for example, if I'm downloading at a rate of 75 megabytes per second, the total network traffic used is actually more than 100 because of the overhead. Okay. Here is just quickly saying that we're going to download all the RNA-seq data from the Cancer Genome Atlas. It's about 65 terabytes of data. It's going to be downloaded next week. We can do that in about 13 days, and there's no cost to this. So this ability allows us to download public data, which we're using more and more. Okay, this shows the wait I/O of when I'm running uploading data to Amazon S3 using Bado. So this again is just a kind of a side effect, if you will. You probably can't see this, but the wait I/O, the top of the wait I/O, the black bars is about 40%. So 40%. So this is a really high wait I/O, and so you want to be careful how you use this tool because it does impact the performance of the file system. And this slide just says that we're still using hard drive for getting data from vendors because it's easier. But that might change as we bring Aspera online. All right. So looking into the future, a few things that we want to do: automation, automating data loading, and also downstream stuff, and the cleanups. There's a couple of different tools that we can use, and we're exploring those. I mentioned earlier that you can archive inactive stuff to cheap storage. We're doing that ourselves. Bring Aspera online. Reference-based compression, this is something that has not been a priority to look at, but it is in the back of our mind. So this is where you just store the difference between the reference and your basis. And as you can imagine, you can potentially save a lot of space, although it is more complicated. And then once, if we ever get the challenges associated with raw data out of the way, that we can spend more time on metadata and sample management. All right, a few key takeaways. In order to understand your storage needs, you need to first understand the analysis. balance risk and cost. The key there is understanding the risk and see if you're willing to accept it, and then you should be confident to throw away the unnecessary stuff. Okay. And this certainly was not something I did by myself. There's a lot of folks that helped me out along the way, so I just want to give thanks to those guys. And that should be the, yep, that concludes my slide. Thank you guys very much. So I think, Sasha, I'll pass it along to Sasha now.
Thanks, Yuhao. Thanks for sharing your insights and what you're doing inside of LIlly to manage next-gen sequencing data. And so we have a little bit of time now to open it up for some questions, and I see that we actually do have a list here. So I will wait for our moderator to put up I think the first one, so everybody can actually see the question.
Yeah, we can go ahead and move over to Q&A now. So here's our first question from the audience. This is either for Sasha or Yuhao. What were the challenges to convincing users and management that it was okay to throw away data?
Yeah, that's a good question. There's a couple of types of people involved. One is the bioinformaticians who are using the data, and the other is the storage admins who are setting the policies. For the users, it was hard for them to really know what data can be thrown away, as I alluded to in the slides, because when we first started doing NGS, it wasn't clear what the analysis looked like, so it was hard to define that. But once we got the analysis cleared up, then we became more comfortable throwing away the stuff that we don't need once we knew what they were. And then the storage admin was very happy to do that because the file system was running out of space. Actually, everyone was quite eager to throw away the unnecessary stuff so they can have more space to work with.
All right, great. And here is our next question. What file types do you compress, and how do you manage compressed or uncompressed delays?
Okay, so we compress the FASTQ files and any other large text files that we find. FASTQ files, we can do that automatically. The others are not, we might have to do that manually. But most of the tools, if not all tools that deal with FASTQ files, take gzipped compressed files. So we always compress the FASTQ files, and that we would like to bzip2 works better in the compression, but not many tools take bzip files, so we end up just compressing the FASTQ files with gzip.
Okay, great. And here's the next question for you. Why are you using internal computing resources instead of the cloud?
Yes. So early on, we did use the cloud for some data processing when the internal capability wasn't as mature. But over time, we found that the cloud added a lot of complexity, so the learning curve was fairly high. And also, early on when we did this, this was about 2 or 3 years ago, we couldn't do everything we wanted to do on the cloud, so we did, let's say, half of the workflow on the cloud, but then we still had to bring the other half internally to do it. So then it just became easier to do it all internally.
All right, great. And here's the next question for you. Have you considered implementing a catalog system like iRods? What is your take on it? How will it be helpful for analysis?
Yeah, iRods has been considered. I think it could be useful, although the part that is arguably most famous for is integration of heterogeneous file systems. And that's not a big use case for us. We would be looking at more for automating things, maybe metadata management, depending on how easy it is to manage that. So it's not clear if it's something we want to pursue, but we are looking at it.
Okay, great. And I think we've probably got time for one more question, so this will be our last question for the day. Do you use Isilon's Smart Pool feature to tier data among cheap/slow and inexpensive fast storage?
That's a good question. So I'm not familiar with the Smart Pool feature. What I do know is that we do have several tiers of storage solutions from Isilon. Some are more high performing and some are lower performing. So we do automatically move data from the higher tiers to the lower tiers based on how old the data, how long the data has not been accessed. So I'm not sure if that's what this Smart Pool is, but we are doing that automatically.
All right, great. And as I said, I think that's our last question for the day. We had a lot of really great questions, and we couldn't get to them all, but we will be getting back to everyone who submitted personally after the webinar. Thank you for attending this Fierce Live webinar and submitting so many great questions. I'd like to thank our speakers for participating and EMC Isilon for sponsoring. This webinar has been recorded. You'll be able to access the recording within 24 hours on the same page that you used to register for this event. Thank you again for joining, and we look forward to seeing you at future events.